Hi, I'm Himanshu Gupta. I'm a student at the University of Colorado Boulder, where I work with Dr. Bradley Hayes and Dr. Zachary Sundberg. Today, I'm going to talk about our paper, Intention-Aware Navigation in Crowds with Extended-Space POMDP Planning. Nowadays, it is fairly common to see autonomous systems in structured settings in the real world. For instance, robotic manipulators are used in confined spaces in factories, and vehicles can drive autonomously on freeways to stay within their lane. However, it is still uncommon to see autonomous systems in unstructured environments with uncertain dynamic obstacles. Navigating through a crowd of pedestrians is one important example of this. To choose a good trajectory to navigate among moving pedestrians, a robot must have the ability to do these three things. It must be able to infer the pedestrian's intention based on the sensor observations that it receives from the environment. For any given intention, it should be able to predict the pedestrian's future behavior. Given the pedestrian intention and a pedestrian behavior model, it should then be able to generate an efficient path from its current position to its goal location that avoids collisions with both obstacles and the moving pedestrians in the environment. Our work can be situated within a body of literature that focuses on the third component of determining the best plan of action for an autonomous vehicle. In recent years, a number of research efforts have focused on solving this problem. Less complex approaches use reactive control schemes, where the vehicle tries to move along a predetermined path and stops as soon as a human comes within some distance of the vehicle. This approach doesn't utilize a pedestrian model and also doesn't account for the delayed effects of the robot's current action. As a result, these approaches often lead to suboptimal decisions. Another common approach is to use a predict and act controller. The vehicle uses observations from the environment to maintain a belief over the pedestrian's goal locations or intentions. It then uses the pedestrian model to obtain the pedestrian's path towards its most likely goal and generates a path to its goal that avoids collisions. However, this approach ignores the uncertainty in pedestrian intention estimation and as a result could lead to unsafe behavior. So, to drive near pedestrians safely and efficiently, an autonomous vehicle must be able to reason over the uncertainty in pedestrian intention estimation and consider the long-term effects of immediate actions. POMDP planning provides a systematic approach to achieve these objectives. Partially observable Markov decision process, or POMDP in short, is a mathematical framework for optimal decision making in the presence of various types of uncertainty. Previous approaches have used the POMDP framework for navigation-centric tasks. The formulated POMDP can be solved approximately either using online solvers that perform tree search to obtain a policy, or can be solved offline using deep reinforcement learning techniques to learn a policy. In this work, we are focusing on using online POMDP solvers to generate a policy. Since obtaining exact solutions to POMDPs is an intractable problem, there is reservation within the field to use POMDPs for large planning problems. As a result, prior work has solved the navigation among pedestrians problem using a two-step approach that decouples heading control delta theta and speed control delta s for the vehicle. Let's visualize this approach. Consider the environment given in this figure, where the black circle denotes a static obstacle. The vehicle observes pedestrians 1 and 2 in its vicinity and maintains a belief over their goals. The first step is to find a path from the vehicle's current location to its goal location. Since it is fairly certain that pedestrian 1 is going towards G2, it puts a potential field around pedestrian 1's most likely path. As it is not so sure about pedestrian 2, it puts a circular potential field around pedestrian 2. The generated cost map is then used by the path planning algorithm hybrid A star to generate a path. The environment state, the belief, and the path are then used to formulate a POMDP for speed planning along this path. The state in this POMDP corresponds to the vehicle's 2D pose, its velocity, and its goal location. It also consists of the position, velocity, and goal location of all the nearby pedestrians. The pedestrian's goal is not known to the vehicle and is the hidden variable in this POMDP. The action space is unidimensional, and the possible actions are to increase, decrease, or maintain the vehicle speed along the provided path, or to apply a sudden brake in the case of an emergency. This POMDP can be solved using any online POMDP solver that performs a tree search. For a long planning horizon problem, it is possible that due to limited computation time, the tree search might never find the sparse positive terminal rewards that are typical in navigation tasks. As a result, the planner can fail to identify good actions. To prevent that, the online planner must have access to an effective rollout policy for every belief node to obtain a lower bound on the value estimate. The despot algorithm is typically used to solve the navigation POMDP since it can handle continuous state space and large observation spaces. Despot builds its tree incrementally by performing a heuristic search guided by a lower bound and an upper bound on the value at each belief node. According to the reward model for this POMDP, there is a positive reward when the vehicle reaches its goal and a negative reward when the vehicle is moving and gets near a pedestrian. As the POMDP controls speed along the given path, all the future vehicle positions during the tree search are going to be along that path. Hence, an effective rollout policy is to execute a reactive controller over the vehicle path as it ensures that the vehicle reaches its goal. The planner realizes that moving along this path at the current time step would potentially lead to a collision and decides that the vehicle shouldn't move. In the meanwhile, both pedestrians 1 and 2 move towards their true goal. The vehicle observes that and updates its belief over their goals. This two-step process is repeated until the vehicle reaches its goal. The animation on the left shows the two-step approach in action. We refer to this approach as limited space planner or 1D A star. It works better than prior approaches, but has two major drawbacks. The decoupling of heading angle planning and speed planning often leads to unnecessary stalling of the vehicle, as can be seen in the animation. Moreover, it is possible that the hybrid A-star path might not be obtained at every time step within the limited computation time. As a result, the system has to estimate the speed over the path from the previous time step. This can lead to suboptimal decision making. In contrast to the decoupled approach, we propose a more effective and general approach to planning for navigation tasks with partial observability and arbitrary distributions. We assert that the POMDP planner should have control over all degrees of freedom that are relevant to the uncertainty it is facing. When navigating among pedestrians, the POMDP planner should have control over both speed and heading, rather than just speed along a predetermined path. Consider the same environment and belief over pedestrian 1 and 2's goals as before. We use this to formulate a POMDP for both heading and speed control. The state for this POMDP is the same as the state for the POMDP in 1D A-star approach. However, the action is different. In our approach, we give the POMDP control over both change in heading delta theta and change in speed delta s. Despot performs a tree search to determine the best possible control for the vehicle. This expansion of the action space opens up a much larger region of the state space to exploration during tree search. The planner is no longer reasoning over uncertainty in pedestrians' intention along just one path, but along multiple possible paths to the goal. This poses a critical challenge to tree search. There is now a need for an effective rollout policy for all the possible future vehicle positions to distinguish good future states marked in green from bad future states marked in red. A rollout policy is considered effective if it could obtain the positive terminal reward, which for this problem translates to finding a path from the vehicle's position to its goal and executing that path using a reactive controller. We generate these paths for the rollout policy by using multi-query motion planning techniques like probabilistic roadmap or fast marching method. Details on how these techniques are used for path planning can be found in our paper. Both these techniques are run offline at a much slower rate than tree search planning. For experiments, our simulation environment is a square field. The autonomous vehicle is modeled as a holonomic vehicle. Its starting position is in the bottom left half, and the goal position is in the top right half of the field. Every pedestrian is trying to go to one of the four corners of the field. We have designed 3 experimental scenarios. Scenario 1 resembles an open field without any static obstacles. Scenario 2 resembles a cafeteria setting with 6 small static obstacles. Scenario 3 resembles an L-shaped lobby with a big static obstacle in the bottom right half. We have compared the performance of 3 different planners. The limited space planner, or 1D A-star, is the 2-step approach that decouples heading and speed planning. It has 4 possible actions for POMDP speed planning. We refer to our proposed approach of a 2-dimensional action space POMDP as the extended space planner. Depending on the choice of the path planning technique to generate the rollout policy, we have defined 2 extended space planners, 2D FFM and 2D PRM. Since we don't yet have effective online POMDP solvers for large or continuous action space problems, we discretize the action set to have a maximum of 11 actions and their condition on the state of the vehicle. For each scenario, we generated environments with different pedestrian densities. The number of pedestrians varied from 100 to 400 in the simulation environment. We ran 100 different experiments for each setting and compared the performance of the 3 different planners. The first key observation from our results is that our proposed extended space planners, 2D FFM and 2D PRM, executed paths that took less travel time on average than the 1D A-star approach without compromising safety. The travel time for 2D FFM and 2D PRM is comparable across all the different settings, which indicates that the sensitivity of travel time to the choice of motion planning algorithm used for generating effective rollout policies is low. In the 1D A-star approach, hybrid A-star generates a path without considering the vehicle's speed and by using ad hoc techniques to handle uncertainty in pedestrian intention. In most cases, the POMDP speed planner realizes that traveling along this fixed path at the vehicle's current speed can lead to a collision. As a result, it decides to either slow down or stop, which increases the total travel time. On the other hand, the extended space planners reason over uncertainty along multiple paths and often manage to find a path where they do not have to slow down or stop. Another important observation is that both 2D PRM and 2D FFM outperformed 1D A star in the metric of travel time, at least 91% of the time across all the different settings. In densely crowded environments, moving to empty spaces nearer to the agent's goal instead of staying idle and letting nearby pedestrians pass is an intuitively good strategy. This behavior is visible from the 100 different trajectories executed by 2D FFM and 2D PRM in scenario 2. The vehicle, when controlled using extended space planners, keeps moving to empty spaces instead of stopping and ends up covering a wider area of the environment in comparison to the case when it is controlled using 1D A star. Extended space planners are also able to take advantage of the wider space on the bottom half of the environment, while the 1D case uniformly avoids the obstacle in the center, oblivious to this. Similar patterns were observed for experiments on scenario 1 and scenario 3. To conclude, our work presents an intention-aware navigation system that uses an extended space POMDP planner to generate efficient policies for an autonomous vehicle among moving pedestrians. Solving a POMDP that controls both degrees of freedom, that is speed and heading, instead of just speed over the hybrid A-star path, results in faster trajectories. This additional control parameter enlarges the reachable state space and raises the need for practical rollout policies from these states during the online research. Our approach uses multi-query motion planning techniques like fast marching methods or probabilistic roadmaps to efficiently generate effective rollout policies. The open source code for our work can be found at the link at the bottom of the slide. Feel free to reach out to us if you have any questions. Thank you.